So this is where we left off. And we were talking about activator and deactivator, and I gave you a rundown of why activators are ortho-para and deactivators are metas. I gave you the basic chemical explanation. It's something that a lot of people don't do. I know that my instructor didn't do it to me when I took organic. I just basically had to trust their word, memorize a chart, and go on. No one really took the time and explained it to me until I did it for myself. But I'm not going to treat you that way. You pay tuition dollars. I'm supposed to be able to do a job, and that job is to teach you organic, and I hope that I'm at least making progress in that. So the reason that we took a closer look at activators and deactivators with ortho-para meta directors is because it's going to be very important in the reactions that they begin to talk about and present to me in this field of benzene and substituted benzenes. All right, so let me show you how easy this is going to be. Let's say that we have a benzene ring. We have a benzene ring and we've added Br2 and FeBr3. What's formed? Oh, well, we learned this in the last lecture module, Tracy. What we learned is that this benzene basically substitutes a hydrogen for an incoming Br group, and we end up with Bromobenzene as a product. Oh, good for you. Good for you. That's exactly what we learned. But that was a benzene. That wasn't a substituted benzene, right? And we've been focused on substituted benzenes. So this was a good review. It's a good starting place at least. Also note that I could put the bromine wherever I wanted to put the bromine. I could go on top. I could go at the bottom. I could go down to the left, down to the right, up to the left. Doesn't really matter where I put it. So basically, you just slap a bromine on it, and I'll slap a check mark on it. I mean, it's as simple as that, folks. All right? But this is substituted benzene land. Okay, so let's say that we have a benzene, and this benzene has a CH3 group on it. Toluene. Hey, look at there. And we'll add Br2, and we'll add FeBr3 to it, just like up above. Now, what's my product? Folks, if you can do the above example as easy as you did it, then you should be able to do this example just as easy. No major difference except for the concept that toluene is a director. The alkyl group of CH3 is a director on this benzene ring. So it's going to tell that incoming group where to go. All right, well, if I forget that, remember I told you you can use this chart. I'm not going to take the chart ever away from you at all. So if I can go back to this chart and I can say, oh, look, there's the R group down here. That R group is CH3. That's an R group. It's a weak activator, but guess what, folks? It's still ortho and para directing. Okay. Well, what that means is that in one version, I'm going to get ready to add on a bromine. Just like I did up here, there's no difference. And that bromine will add on to an ortho spot. I just chose the right-handed one. You could have chose the left-handed one too, if that's what you wanted to do. It's the same molecule, it doesn't matter. Just put it on there in an ortho. But it's a ortho-para, which means it can also slap the bromine there. So here we get two different products. And folks, there's nothing that I can really do about it. It's just going to happen that way. Sometimes it will slap it on an ortho. Sometimes it will slap it on a para. It's just like almond joy. Sometimes you feel like a nut and sometimes you don't. And that's what this benzene goes through. So here we have toluene, and toluene reacts with diatomic bromine in the presence of iron 3 bromide to make a mixture of two different products. One product being 2-bromo-toluene, and the other product being 4-bromo-toluene. Look at how beautiful that was. If I didn't want to use the word toluene because IUPAC says, no, you can't use toluene no more. Okay, whatever, IUPAC, I can make this change, and what I'll do is that I can go through and name this just as a methyl group. So B comes before M, and that would mean it would be called 1-bromo 2-methyl benzene. So whatever. And then the other one, bromine still comes before methyl, so 1-bromo 4-methyl toluene. Or, no, sorry, benzene. So toluene reacts with diatomic bromine in the presence of iron 3 bromide to form two products. One of those products could be 1-bromo 2-methyl benzene, and the other one could be 1-bromo 4-methyl benzene. There you go. Simple, easy, breezy, clean, nothing new. It's just a concept of where do I add the group to? That is it. Where do I add the group to? All right, so let's take a look at another example. Let's say that we had a benzene. There it is. Notepad, glitchy notepad. The notepad is getting as excited as me. All right, so now let's take a look at this benzene structure. So we've got this benzene. The benzene's going to have, this time, a bromo group on it. And we're going to add Cl2 with FeCl3. And they want to know what product would be formed from this reaction. Okay, so we use basically what we have been learning throughout the past two lecture modules. And it's going to look at this product and it's going to say, okay, the bromo is not going to get changed up, right? The bromo doesn't get touched. The bromo is there. The bromo has claimed its territory on the benzene ring, and it says, I'm not going to go anywhere. But chlorine, if you move in, I'm going to tell you where to go. Okay, so that bromo group, I've got to figure out, is it ortho-para or is it meta? Well, the halogens are deactivators. But keep in mind, the halogens have electron pairs. And that is why they are still a ortho-para director. They are not a meta. Even though they deactivate the ring, even though they make it a little bit more stubborn to react with, they are still an ortho-meta director. So that means in this reaction, when I add the chloro group, because that's what this combination does, it's going to add the chloro group here, or it's going to add it at the para position, which is going to be there. Okay, so if I go through and name each one of these, let's name them. With this one, okay, B comes before C, so I could call this a 1-bromo 2-chlorobenzene, all kind of one word. And the one over here to the right, B comes before C again, so it's still a 1-bromo, but this time it's a 4-chlorobenzene. If I don't want to name it that way, there's another way I can name this thing. These two groups are ortho of each other, right? So I could do an O-bromo-chlorobenzene. And then over here to the right, these two groups, they're para of each other. So I could write P, bromo-chlorobenzene. So in this reaction, bromobenzene reacts with diatomic chlorine gas in the presence of iron 3 chloride as a catalyst to form two products. One product is 1-bromo 2-chlorobenzene, also known as ortho-bromochlorobenzene, and the other product is 1-bromo 4-chlorobenzene, which is also known as P-bromochlorobenzene. Folks, there you go. Again, a very nice wrap of everything that we've been learning in this module, and then a review yet again of what was in the previous module. All right, let's take a look at another one. Here we'll have a benzene, and this benzene is going to have a C double bond O with an OH. And we're going to react this with HNO3 and H2SO4. And we want to know what happens. What kind of product am I going to get from this reaction? Use the rules. Use what we've talked about up to this point. I'm going to look at that benzene with the C double bond OOH. You remember what that was called? That C double bond OOH was a carboxylic acid. That's benzoic acid. Right there, it's benzoic acid. So benzoic acid is going to react with nitric acid in the presence of sulfuric acid as a catalyst. Well, we know that benzene is going to be part of the product. We also know that this C double bond OOH is going to be part of the product. Folks, I don't have to worry about that H leaving. The reason is because I know it's an acid, but I'm putting it in the presence of other acids. So my pH is going to be very, very low. Nitric and sulfuric acid, folks, they're pretty strong acids there. So I don't have to worry about any of that hoodoo-y stuff going on about losing a proton and writing a negative charge and blah, blah, blah. It's acidic conditions, keep it an acid. However, C double bond OOH. Let's just look at the structure. I don't need the chart. That carbon is seeing two oxygens. And each one of those oxygens, second, all the way through. Gotta keep forking out. That poor carbon's going to be partial positive. Because that poor carbon is partial positive, it does not want that carbocation to form at the carbon that it's attached to. So this is a meta-director. It is a deactivator. All deactivators are meta-directors, except for the halogen groups, right? Again, if I need the chart, I can go back to the chart and find that. C double bond OOH. Look at there. C double bond OOH. Let me see if I can find it. Well, this is the activator side. Don't really find it here, right? Okay, so let me go to the deactivator side. C double bond. Oh, look. No, that's close, but no cookie. Here it is. C double bond OOH. It's right there. So this is a deactivator. And that deactivator means that it's a director, a meta-director. So in this example, what you'll see is that that carboxylic acid group is going to say, okay, nitro, that's fine. You come in, move right on in. We'll give you a room. But it's going to be a meta. All right, well, O-M-P, Becky, Mecca. Meta's right there. Or you could have went the other way and put it on the other side. It doesn't really matter. I don't care. Just put it in a meta spot. And what goes on? Well, when we add nitric and sulfuric as a combo, it's the NO2 that goes on to that position. Now, let's figure out how to name this. We already said that the benzene with the C double bond OOH was called benzoic acid. All right, so we're going to keep this, and that also means that that automatically is spot number 1. So spot 2, spot 3, I'm going to have a nitro group. So 3-nitro benzoic acid is going to be the name of that compound. If I didn't want to use the number 3, I could also use M for meta. O-M. That's M-nitrobenzoic acid. All right, so let's take a look at an example problem. What products, in parentheses an S, meaning could be more than one, result from the nitration of each of the following? propyl benzene, bromobenzene, benzaldehyde, benzo nitrile, benzene, sulfonic acid, cyclohexyl benzene. If I had talent, I could probably make some kind of song out of that and walk away a millionaire. So, nitration. They are telling me that in each one of these cases, I am adding HNO3 in the presence of H2SO4. Every single one's going to be treated the same. Nitration. Okay. So, I'm first going to start with A. Propyl Benzene. Okay. So, let's draw propyl benzene. There's the benzene. Propyl, 1, 2, 3. 3 carbons. I'm not going to draw the hydrogens. You could have drawn this as a skeletal zigzaggy thing if you wanted to. It doesn't matter. I don't care. Just put 3 carbons on there. So if this undergoes nitration, the addition of nitric and sulfuric acid, what is a propyl group? A propyl group is an R group. I need to find the R group on the chart. When I find it on the chart, it's going to tell me that it's an activator, and because it's an activator, it's automatically going to be meta. No. It's automatically going to be ortho and para. That is what the activators do. So, 1, 2, 3, and I know it's got to be 1, 2, 3. I'm going to get a mix of ortho and a mix of para. Just to prove a point, I'm going to slap it on right there. That's ortho, right? I can go either way. So there's a nitro group there. And then para, O-M-P. So there is the NO2 group that goes there. If they wanted me to name them, I could. That might be part of the thing. I never can forget that. Again, it's a build-up process. It's a foundation, and I'm building on top of my foundation. The next is bromobenzene. Kind of already done this, but we'll do it again, folks. There's bromobenzene. Okay, bromo is a halogen. Halogens are deactivators, but they are the only deactivators that are going to be ortho and para. And the reason is because they have those electron pairs, and they can participate in the delocalization. So it's good for them. So if I'm going to nitrate bromobenzene, then that means ortho, I'm going to have an NO2, and para, I'm going to have an NO2. So once more, I'll have 2 different choices, an O and a P. All right, so for part C was benzaldehyde. All right, so benzaldehyde is the benzene ring, and this is a C double bond O with an H. There's the aldehyde group, so paired with benzene is benzaldehyde. Get it? Okay, so now we've got to add nitric acid. We're going to nitrate it. We've got to figure out what it does. Well, that carbon, just by looking at it, the oxygen's going to suck that carbon of the electrons. That carbon doesn't have a free pair of electrons that it can participate. It doesn't have anything that it can donate to that ring. And if I find the aldehyde on that chart, and it's there, here's the deactivator side. Look, right up here. C double bond OH. It's right there. We know that it is a deactivator and it's a meta-director. So in this example problem, that means when we nitrate it, well, that aldehyde group's not going to go anywhere. It's going to stay there. And we're going to put it at the meta position. OM, right there. So there is the NO2 group. I could have went the other way with the ring. It still would have been correct. No big deal. All right, the next one. The next one they gave me was Benzo Nitrile. Okay, so here's the benzene ring. And nitrile is a carbon with a triple bond and an N. So we're going to nitrate this group. We're going to add the NO2 on. They kept it the same to kind of make it easy for us. So let's say that I don't really know. I mean, I look at this carbon folks, that carbon is getting pulled of those electrons by the nitrogen. I mean, look at that triple bond. The nitrogen is a big sucker, and it's going to suck those electrons on its end, and it's going to expose that carbon as a partial positive charge. Well, if I did not know that, I can go to my chart, and I can find C triple bond N, and look, it's right here at the bottom, and that is a strongly deactivating group, which means that this is a meta director. So with this reaction, what that means is that nitrile is going to stay where nitrile's at, right? It's already marked the territory. It's already moved into the room. And when the nitro comes in, it's going to say, buddy, you need to go to the meta room. All right, so ortho meta right there. And this is the NO2. Thank goodness it's not the red room. It's the meta room instead. Okay. Next is benzene sulfonic acid. So here's benzene. Sulfonic acid is SO3H. Oh gosh, that sulfur is getting pulled with 3 oxygens. So you can probably imagine that this is going to be a slightly positive atom because all of those oxygens are electronegative and it is sucking those electrons away from that sulfur no matter what. And if I look at this chart, I'm going to find SO3H down here toward the bottom. That is a strongly deactivator group, and that is also a meta director. So in this example, that basically means I'll take my benzene ring, I'll redraw it, I'll put my SO3H up there, and this is a meta OM right there, and the nitro group is going to go in that spot. All right, so finally, the last one that they tell me to work with is Cyclohexyl Benzene. Ooh. All right, so benzene, there we go, and it's cyclohexyl on it. Well, I'm just going to choose here, and cyclohexyl means a 6-membered ring. It's not a benzene. There's no double bonds. There's no delocalization. It's just a 6-membered ring. That's all there is. What on earth is this going to be? Okay, well, if you don't know, that's fine. We'll go back to the chart. And here we go. And if I go to the chart, I see at the very top NH2, NHR, NR2, OH, OR. We don't have any of those yet. NHC double bond O, OC double bond O, and then an R. And folks, that's what cyclohexyl is. It's a random alkyl group. It's a cycloalkyl group, but it's a random alkyl group. So that means that this cyclohexyl is a weak activator, but it's a ortho-para director. I'm going to get 2 sites of attachment here. Now, do not get that confused with this. That AR is aryl, which means there is a benzene attached to a benzene. That is an aromatic group. That is what AR stands for. It's aromatic there. So cyclohexyl is the R, and that means this is a ortho and a para director. So with this reaction, 2 products are going to get formed. A cyclohexyl on a benzene that is ortho, so NO2, and a cyclohexyl that is on a benzene that is para, which is NO2 at that spot. Now, with this said, this kind of follows up something that we're getting ready to talk about next. And it's this whole idea of O and P. And we've got a question, is one preferred over the other? In all of these example problems that we've talked about, if you've noticed, we've just been drawing down the possibilities, and we've not really been identifying if one was more preferred over the other. Meta, I don't have a choice. It's just what it's going to be. It's going to go there. Sorry, it's going to go there. Move on. But when O and P has a possibility of forming, does the molecule prefer one over the other? And the answer is yes, it does. So in these past three examples, what we did is that this was a meta director. This was the only choice that we had. That was it. Those are easy. This one was a meta director. This, again, was the only choice that we had for that reaction. That was it. We move on to the next one. But this last example that they gave me, and some of those examples in the beginning of the example problem, they were OPs. We wrote down both. We put a plus, and this one and that one, this one and that one, in all of those scenarios. This was the ortho, this was the para. So what we need to discuss now is once we form these, great, check mark, ding ding, you get it right. You get partial credit at least. Can I pick out which one is more preferred over the other? Or is it really always a 50-50 split? And the answer, of course, is no. It's not. You knew that was a false statement. You knew I was building up to that question to give you the proper answer that you knew that was coming to you. It will not be a 50-50 split every single time. So we need to talk about the decision-making process that goes into the next step of these reactions. And if O and P are formed and we get both, can we identify the major product from that reaction? Will it be O or will it be P? And in the next video, you'll find out how we do that.